4 weeks remain until the sky welcomes 2026. Millions of fireworks are being prepared to ignite that moment. One can notice the sheer volume of material awaiting its turn. But this is just the beginning. Why are such intricate steps needed for explosions that last only a few seconds? The brilliant flash vanishes instantly. Behind every burst lies an entire craft-driven journey. It seems superficially simple, but in reality, the process spans from chemical mixing rooms to star-forming lines. The camera glides past tightly controlled assembly areas where components meet. It is visible how lifeless ingredients are primed for the future. The silent world of production ensures the beauty of the light. A few dozen degrees of deviation is the critical threshold that determines the success of blue fireworks. Why is this specific shade one of the rarest colors to ever appear in the night sky? To the observer, it looks like a standard pyrotechnic effect. However, copper compounds must burn within an extremely narrow temperature window to sustain the hue. Any excess heat shifts the chemical reaction, turning the burst into an unintended green or a washed-out white. But this is just the beginning of the technical difficulties. One can notice that even in the age of automation, modern production relies heavily on traditional hand craftsmanship. Skilled artisans manually control the consistency of the mixture to ensure stability. Each individual star is carefully mixed, pressed into molds, and dried on racks before assembly. At first glance, this manual work seems peaceful, but behind the beauty lies a silent layer of chemical risk. Materials containing barium or copper become harmful if fine dust is inhaled over long periods of exposure. Consequently, workers operate in strictly regulated short shifts and utilize full protective gear to filter out particulates. Industrial air filtration systems run continuously in the background to capture the remaining dust. This ensures the environment remains safe for the ongoing process, thousands of times. Exactly how often the color formulas have been tested before a single gram of powder enters the production line. Technicians operate inside an isolated mixing room where the ventilation systems run continuously to keep the air safe. Why is such constant airflow required in this quiet environment? The room appears still and the work seems delicate, but this is necessary to prevent volatile dust from accumulating, ensuring the safety of the entire facility while the powders are weighed. Ultrafine charcoal powder sets the burn rate, sulfur maintains the reaction's stability, and potassium nitrate acts as the oxidizer that allows the mixture to ignite at exactly the right moment. Technicians add highly purified metal salts during the color-making stage to create specific visual effects. One can notice how strontium creates red hues, while barium produces green, sodium provides yellow, and copper nitrate generates the rare blue tone. Once the ingredients are roughly blended, the entire batch passes through steel sieves with extremely fine mesh. The smooth powder falls through like a stream of black sand, while any clumps or oversized particles remain on the screen. At first glance, this looks like simple filtration, but in reality, it brings every grain to a consistent size to ensure even combustion. Without this step, hotspots could form, distorting the color or destabilizing the burn. Therefore, only after reaching the proper fineness is the mixture loaded into large steel drums for thorough blending. These drums rotate slowly for hours, allowing every particle to coat and bind evenly with the others. But this is just the beginning. The result is a fully uniform, safely refined powder, pure enough to become the heart of the pyrotechnic stars. The mixture moves to the pressing area, where specialized hydraulic machines compress it into raw cylindrical pellets. Technicians load the powder into multi-cavity metal molds, where each cavity forms a pellet significantly larger than the final burning grain. The press descends slowly and holds pressure for 3 to 5 seconds. This duration ensures each pellet achieves a stable density, avoiding a structure that is too porous which would crumble, or too hard, which would hinder later shaping. When the pressing cycle ends, the mold opens to reveal rows of dark matte pellets packed across its surface. Workers gently tilt the mold, allowing the pellets to slide onto wooden trays lined with anti-static paper to further reduce spark risk during transport. The process is only gaining momentum. These trays sit on multi-tier racks in a temperature and humidity-controlled room, awaiting the coating stage. Once the raw pellets have taken shape, they are transferred into a rotating drum made of stainless steel to stabilize their surface. The equipment is typically positioned at a 30 to 45 degree angle. Technicians load the pellets and switch on the slow rotation mode to increase durability and ensure a uniform burn rate. As the drum turns, they spray a thin binder solution or dust on additional dry powder depending on the requirements. One can notice how the binder strengthens the outer layer, preventing each pellet from chipping during handling. If a larger grain size is required, technicians alternate between spraying binder and adding powder through multiple cycles. Each layer increases the diameter by only a tiny amount, but after many rotations, the pellets gradually grow to the precise size needed. It gets more complex further on. The rotation speed is kept intentionally low to avoid excessive friction, while allowing the coating to spread evenly across each surface. Coating and rounding typically lasts anywhere from 20 to 40 minutes for basic shapes. However, for the layered growth used in aerial display shells, the process can extend to 2 or 3 hours to ensure uniformity before the next stage. Once the rounded stars finish their coating, they move into the drying stage. Technicians spread the stars into a thin, even layer across wide trays, ensuring each piece has enough space so they do not stick together. In modern factories, drying takes place indoors at temperatures between 77 degrees Fahrenheit and 86 degrees Fahrenheit. Humidity is kept stable so the binder layer dries slowly without cracking. In more traditional workshops or large-scale operations in Asia, the stars dry under direct sunlight, but always beneath an open-sided canopy. This shield prevents rain exposure and protects the stars from overly harsh sunlight that could cause rapid evaporation. Workers rotate or reposition the trays throughout the period, so every star receives an even amount of heat and airflow. Total drying time can range from several hours to more than one full day, depending on the weather conditions or the thickness of the coating. The production line now splits into 2 separate paths, corresponding to the tube-style fireworks and aerial shells used in professional displays. 2 types of durable material, rolled craft paper and composites, form the body of every firework tube. These cylinders are explicitly designed to withstand the immense high pressure generated at the moment the lift charge ignites. Technicians begin the assembly by loading the dried stars into these containers using a funnel or a simple wooden scoop. One can notice how they gently guide the combustible pellets into the tube to avoid any hard impact against the rigid inner walls. But this is just the beginning. Why is the amount of stars placed inside each tube strictly calculated by a formula? At first glance, filling the tube seems like a matter of simple volume estimation rather than precision counting. However, the specific quantity directly dictates the visual effect, creating either a single streak with fewer stars or a dense, vibrant burst with a higher count. Technicians strictly monitor every production batch to maintain a consistent star quantity across all tubes, preventing any visible variations during rapid-fire sequences. Workers carefully clean the tube opening and inspect the interior to ensure the stars sit correctly without tilting. It is visible how the components align without touching the inner walls before the process moves forward. Everything only gets more complicated. It seems simple to add propellant, but in reality, the lift charge requires black powder in a coarse grain form rather than fine dust. This propellant is significantly larger than the fine powder previously used to mix the stars. One can notice the dark grains pouring through a funnel to settle at the base of the tube. Because even a few extra grams or a few grams too little can directly affect the height the stars are able to reach, the measurement adheres to a fixed specification. A wooden or plastic tamping tool carefully presses down to secure the lift charge, compacting the granular layer without damaging the delicate stars above it. Once the powder is compressed, technicians verify the total height inside the tube to ensure the distance between the stars and the lift charge matches the intended design, guaranteeing the stars leave along the correct trajectory. Transition to the next level. The fuse dictates exactly when the firework activates, demanding more caution at this stage than in almost any other part of the assembly line. Each tube arrives at the mounting station, where workers cut the fuse to a standard length. They select between a slow-burning fuse for a calculated delay or a fast-burning variant for sequential effects. Workers insert the end of the fuse into the mouth of the tube and fix it firmly in place with a craft paper wrap or a specialized adhesive. One can see the final step as the tube opening is sealed with a pressed paper cap or a thin plastic cover to protect the interior from moisture. The assembly is now secure, with the stars held firmly in position for the future launch. Two hemispherical paper casings made from compressed pulp form the foundation of the aerial shell. The production line moves on to this complex pyrotechnic device after the tube-style fireworks are completed. Technicians mold the material into shape so it can withstand the pressure of the explosion. Why mix ordinary rice hulls with the dangerous black powder in the core? At first glance, it seems like a cost-saving measure to use agricultural waste. But in reality, the hulls pre-soaked in explosive powder create critical porosity within the burst charge. Technicians prepare the fully dried stars and sort them carefully by size before assembly begins. The time fuse has already been installed at the center of the hemisphere. Stars are arranged in concentric rings around this fuse to ensure a perfectly rounded flowering pattern across the sky. One can notice how the arrangement differs depending on the intended effect, because a single ring produces a simple burst, while 2 or 3 rings create a denser, fuller explosion. Specialized patterns are designed to create shapes such as hearts or chrysanthemums. Technicians inspect the spacing between every star to ensure none of them touch. Therefore, the risk of off-center burning or premature ignition is eliminated. Technicians pour the burst charge into the cavity between the 2 layers of stars. This component acts as the core responsible for propelling the stars outward in every direction. The rice hulls help distribute the explosive force evenly during the burst. They fill the entire central space without packing it too tightly. But this is just the beginning. The density of this layer is critical for the final performance. If it is too loose, the shell bursts weakly and the effect becomes sparse. However, if it is too compact, the internal pressure rises too high. The shell may break unevenly or off-center during the explosion. Technicians level the burst charge carefully so that every star receives the explosive force evenly. The 2 hemispheres are joined together to form a complete sphere. Immediately after the halves are aligned, a ring of adhesive is applied around the base of the time fuse. Workers wrap it tightly with craft paper string to seal the fuse entry point, because a solid airtight joint is required to prevent gas leakage during the burst. It is visible how the entire seam is reinforced using paper glue or a starch-based paste. Multiple layers of craft paper are wrapped around the shell to increase its structural strength. The number of layers depends on the shell size. A 3-inch shell typically requires only a few layers. 6-inch to 8-inch shells demand many more to withstand the higher internal pressures. It gets more complex further on. Technicians press the surface of the shell gently to preserve its perfect spherical shape. They smooth each layer of paper firmly to ensure there are no trapped air pockets. This prevents any deformation that could destabilize the flight path. But regardless of the type of firework, none can leave the factory without a full inspection. Technicians perform the most essential measurements in the inspection area. They check the weight of each shell and the thickness of the paper layers. The air tightness of the casing and the condition of the fuse are rigorously examined. The placement of the lift charge is also verified. The camera glides along the batch where random shells are selected for live testing. These samples are brought to a dedicated test range and placed inside a steel test mortar. Engineers equip the site with measuring devices such as high-speed cameras, pressure sensors, and altitude meters. The goal is to verify 3 key parameters. They measure the exact timing of the time fuse, the altitude the shell reaches, and the spread pattern of the burst charge. Once all inspection tests meet the required standards, the batch moves to the packing area. Here, each firework is sorted again according to its diameter, effect type, and batch number. Workers seal each carton securely and transfer them to a separate storage zone. Temperature and humidity are continuously controlled to prevent moisture absorption or degradation of the pyrotechnic compounds. From this point, the packaged fireworks are loaded into specialized shipping containers. Licensed trucks approved for transporting flammable materials take the cargo. The fireworks are now ready to be delivered to ports or professional operators. Millions of tiny grains of black powder act as the volatile foundation for every calculated aerial display. Finished products travel strictly to secured ports or directly to licensed professional fireworks operators. One can notice how the transport containers are sealed to protect the sensitive cargo from moisture and friction. But this is just the beginning. Why is every stage of production subject to such rigid testing protocols? To the uninitiated, it looks like simple manual assembly. This is necessary because every shell that rises into the air must function perfectly after hours of mixing and pressing. A single error in sealing or shaping renders the entire device useless long before a spark is ever lit. At first glance, the process seems like ancient tradition, but in reality, it is engineering pushed to its limits. It is visible how artisans transform raw materials into precise geometric structures inside the casing. The brilliant bursts that paint the night sky serve as the result of patience and generations of craftsmanship. And this is not the limit. The explosion fades into darkness, marking the calm end of the technological cycle.